Hello again everyone. Welcome to another mobile robotics video. We left off on sensor classification, so now we're going to continue with dynamic range, and we're still on sensors. So dynamic range is it's a way of measuring the spread between the lower limit and upper limit of input values a sensor can take while maintaining its operation normally. This can be formally defined as the ratio between the maximum input value to the minimum measurable input value. So but we often use decibels, which are used not only for sound but for measuring electric signals, which is usually what's useful with mobile robotics. So because the ratio can be a massive number, it can be quite unwieldy. Decibels are logarithmic, so an increase of say 1 decibel, maybe an increase, well, it's going to be an increase of more than 1 times as much. So for instance, if we were to have a motor that can register values from 1 milliamp to 20 amps, then the dynamic range of this motor would be 10 times log 20 over 0.001, because 20 is the maximum number of amps that it can measure while maintaining normal operation, and 1 milliamp, which is 0.001 amps, is the minimum, which would be 43 decibels if you calculate that. Right. So the next thing we can look at is resolution, and resolution is something you've probably heard of. Sorry about that. It's effectively the minimum measurable difference between two values, such that they end up as two different values when they're detected by the sensor. So it's the min difference between values that can be detected by the sensor, such that these values are seen as different by the sensor. This is usually, but not always, the lower limit of the dynamic range. And after this, we have linearity. And these are all sort of characteristics that we need to know about sensors. So linearity, it governs the behavior of sensor output signals. So for instance, the sensor output signals may be sort of erratic. They may be massive have a massive increase for a certain increase in input, and then a smaller increase, for instance, for the same increase in input. That's why we want to keep the output linear, so we can it's easier to work with the output if it's linear, basically. So linear output means if there are two outputs, X and Y, if there are two inputs, X and Y, and there are two outputs corresponding to these, or Fx and Fy, then for any values of A and B, Fax plus By must be equal to A Fx plus B Fy. There should be brackets here, but you get the idea. And effectively what we end up with is the input-output relationship is a straight line. If you were to plot the input-output result on a graph, then it would be a straight line. The output would increase linearly with the input. And next we have frequency / bandwidth. So this is used to measure the speed at which information can be relayed, or the speed at which the sensor can output whatever it needs to output. And if we define this formally, this is the number of measurements per second of the sensor. Okay, and an important thing to note regarding the frequency is that the mobile robots speed limit is often set by the bandwidth of the robot's obstacle sensors. So it won't be able to go faster than, even if it is able to go faster than a certain amount, it won't, because it won't be able to detect whether there's an obstacle there and be able to stop in time. So the next thing to be concerned about is and let me just make this a bit bigger. It's in just a second. I think we've got, okay, yeah. Okay, so in Situ Performance, I'm not 100% sure how that's pronounced. That's what I was looking up. So performance. What this means is effectively the difference between laboratory performance, like the readings, the performance of the robot in a controlled environment in a laboratory versus the readings of the robot in a real world environment where there's many variables that can be considered. So these characteristics, all of these which we've considered now, these characteristics are they can be like reasonably measured. In a lab environment. Where the external variables and can then be reasonably extrapolated to real world performance. So we can measure all of these in a lab environment and then effectively, maybe make some tweaks and assume that they work. Those tweaked values work or will be the same for the robot's real world performance. So we can, whenever the robot is doing its work, whatever it happens to be doing in the real world, we can assume that it is, or its measurements are going to be correct, at least concerning these characteristics. But there are other characteristics where the real world performance is not going to be the same as the laboratory performance, effectively. So, for instance, sensitivity, which is a measure of the degree to which a small change in input is going to result in a change to the output. So is it a small change going to result in almost no change in the output? Is it going to result in a massive change? So formally, the ratio of output change to input change. And then we have cross sensitivity, which is effectively the sensitivity of the robot to what it needs to be measured, while disregarding and being insensitive to any other properties, any other variables. So the technical term for this is effectively its sensitivity to environmental parameters are orthogonal to the target parameters for the sensor. So, for instance, if a magnet is a magnet can be used to make a compass point north. That's how compasses often work. So it is useful in that regard. But if there's, say, an iron building nearby, or a steel building with iron in it, the magnet might not work because it's cross-sensitive, and the environmental parameters are not orthogonal. So yeah, I think that's just about enough for now. And next time we should be continuing with more characteristics of the mobile robotic sensors, for instance with error and accuracy. So thank you very much for watching, and I hope you have a great day. Bye bye.